Hello there, it's good to see you. We're going to talk about gases today. So if you've ever smelled skunk, you know that it's a horrible smell. And we can figure out gases kind of from how a skunk works. You can have the spray from skunks just be able to move away from the skunk without even having wind or anything like that because gases move in a particular way. So we're going to talk about the nature of gases in this section. So there's three assumptions we make when we talk about the kinetic theory that applies to gases. And kinetic means moving, so anytime you're moving, you're doing kinetics, and so you're moving around. That's motion. And the energy an object has because of motion is called kinetic energy. So gases have lots of kinetic energy. All atoms have kinetic energy, but gases have the most. And we know that we think of gases and all atoms and molecules as being particles, small little dots that are moving. So gases are moving a lot, and they're always in motion. They're always moving. They're never stopped. So according to kinetic theory, the particles in a gas are small, hard spheres with a very, you don't even need to worry about the size of them, the volume of them, how much space they take up. We're just thinking of kind of like as if you've ever played pool or anything, maybe skee ball or something like that, where you're moving that hard sphere. It's really like those tabletop skee ball games where you're trying to hit something into the end pocket. Gases are really like that. So they're hard spheres. They're like pool balls or when you play that tabletop game at the arcade where you're trying to get the little disc in the end of the table. Gas particles are really like that. And the particles move on their own. They're rapid, constant, and random. They're moving all over the place. And they do hit into each other. So when they do, it's like two pool balls on the pool table. They hit, and then they bounce off, depending on the angle that they hit each other in. And the gases hit, they make collisions, and then they bounce off each other, and they don't lose any energy, so that's called elastic. So gases are in a rapid, constant motion. They're always moving, but they are all also hitting the sides of the container, and they're hitting each other. So the little stars are trying to show that. And gases move in a straight line path. It's just like when you play pool and you have the cue and you're hitting into the cue ball, it moves in a straight path. So you have to know geometry to be a good pool player. Gases fill the entire container that they're in. So this is bromine molecules, two bromines. Remember, bromine is a diatomic. It likes to stay in two bromine atoms together into Br2. And here's that vapor. This is a small view of that. They're bouncing around inside this container. There's a little bit of solid bromine on the bottom, but most of this bromine is gas, and it's bouncing around the container. It fills the entire size of the container. So gas pressure is when the gas particles hit the side of the container that they're in, and the force depends on how many gas particles are hitting a particular square inch or square centimeter side of that container. So that's how we measure gas pressure. If there's no gas somewhere, we call it a vacuum. So if you think of outer space, it's pretty much a vacuum. There's hardly any particles moving around in that area, so that's called a vacuum. Atmospheric pressure is the number of collisions that are hitting the side of your container per the space that you have. So per every square inch, how many, or every square centimeter, or every square millimeter, how many collisions of atoms are happening. So this pressure is the simultaneous collision of billions of particles of gas hitting the side of the container. So you can think of it as a balloon. You blow into the balloon, all those little particles of gas that you've blown in there are hitting the side of the container and making that stretchy feeling you feel on the outside of a balloon. If you push on it, you feel that pressure against your hands, and you can press in, but the balloon wants to press out, so that's gas pressure. We can measure pressure with a barometer, and this is measuring the pressure that we have at the atmospheric pressure at different places on the Earth. So at sea level, which we're pretty much at sea level on the delta here, maybe a few feet up, but we're pretty much near sea level compared to most places on the Earth. So we should expect to have this much pressure, this barometric pressure. This is the standard pressure that we associate with sea level. It's 760 millimeters of mercury. The outside pressure is pressing down on this mercury. So the pressure of the gas is hitting, all those particles are hitting this mercury, this pool of mercury, and that's pushing the mercury into this evacuated tube. There was a vacuum at the beginning, and there's no gas inside here, and it pushes this mercury up, up, up. So this is how we measure pressure, atmospheric pressure. So at sea level, we're at 760. If we were on the top of Mount Everest, there would be less of those gas particles pushing down because we're at a higher elevation. We're closer to outer space. There's less gas particles pushing down. So it's only going to go up to 253 millimeters of mercury. That's why people have trouble breathing on Mount Everest, because there's not very much gas up there. And there's even less oxygen within that whole amount of gas pressure. So that's what atmospheric gas pressure is. So remember this number, it's important. 760 millimeters of mercury at sea level. That's called standard pressure. So we call how we measure pressure is we measure it in different units. We can measure it in pascals, PA. That's the SI unit. We can also measure it in different units. So a lot of time we'll use ATM or millimeters of mercury. So we can have a gas problem in any one of these units. You have to be able to convert from one to the other. STP is going to be 760 millimeters of mercury. So that's an important thing to remember, because we use that a lot in gas problems that were at 760 millimeters of mercury. So remember that one. So this is another thing to have memorized on your note card, so you can remember how to change from one to the other. They're all equivalent to each other, so 1 atmosphere is the same thing, 760 and 101 kilopascals. So we just have to know those and be able to convert from one to the other. So that's like a basic kind of problem with the quasar test, converting from one type of pressure to another. So let's try one. So we have 450 kilopascals. We want to be able to change it into the other two units. So let's see if we can try that. So the given is 450, two significant figures, 450 kilopascals, and we're going to use these two conversion factors to be able to convert between that kilopascal. So we always want to put our conversion factor with kilopascals on the bottom to get rid of the given kilopascals. So let's show them out. So this is a basic kind of problem you need to be able to do. And so practice this. This was 450 kilopascals. We're going to use that conversion factor of 101.3 kilopascals in 1 ATM. Take this in your calculator, 450, divide by 101.3, and you'll get that, 2 sig figs. So make sure you can do these problems quickly and you know how to do them. If I want to go to millimeters of mercury, I take the kilopascals, put that conversion factor on the bottom to get rid of these two units, and then put the one I'm trying to get to on top. Put this in your calculator first, multiply by that, divide by that, and you'll get this in your calculator. But we only have 2 sig figs here, so I got to round to, this is showing 2 sig figs, so you could leave it this way because there's no decimal place, or you can show it with scientific notation. So 1, 2, 3 places I moved that dot, so I got to put a 3 right there. Okay, so that's how to do conversions in units. So be able to do all 3 conversions from all the different units. So here's a one to try on your own. See if you can try this one yourself. And there's lots of calculators online. You can ask for a air pressure calculator and say kilopascals, atmospheres, and millimeters of mercury, and you can see how to go from one to the other. It will show you if you got the right answer. So what's the relationship between temperature and energy? So in gas pressure, if you ever see a gas problem, you always have to change to Kelvin for this reason. These are, no. So we'll talk about it in a sec. But we always want to change gas problems into kelvins. So every particle that we see in a gas may not be the same velocity as other particles in the gas. And so we generally talk about the average kinetic energy of a gas. So most of the particles are somewhere in the middle of this range. So if I look at percent molecules this way and kinetic energy this way, there's going to be, if we're at like a lower temperature, which is lower kinetic energy, we're going to have more of a sharper distribution. If we're at a higher kinetic energy, we're going to see more of a wide distribution. Average kinetic energy, which is the temperature of the molecules, is going to be somewhere, most of them are going to be here for this lower temperature, and they're going to be here for this higher temperature. But you're still going to have some particles that are really low speed and some that are really high speed. So when we talk about kinetic energy, we're really talking about the average kinetic energy for the whole set of molecules, not the distribution. So as you get higher and higher kinetic energies, you're going to have a wider distribution of the kinetic energies of the particles. So we talk about gas laws. We always use something called absolute zero. We use degrees Kelvin, which is a measurement of motion. And at 0 degrees K, if we could get to that point, which is the same thing as this in C, we would have theoretically no motion. And it's hard to do that in real life, so we've gotten close. But particles with no kinetic energy would have absolute zero. So it would have a 0 degrees Kelvin number. We've never been able to get there, but we've gotten pretty close in real life. And Kelvin temperature is the direct proportion of the average kinetic energy of the particles in the substance. So that's why we have to use Kelvin in gas laws, because it's a direct relationship, Kelvin, to how much kinetic energy the particles have. And it's a good relationship, and it makes the math turn out for our gas law problems. So they've tried to get down to absolute zero, and their scientists have gotten really close, but we haven't gotten there yet because it's super difficult. So let's see how much you got out of this section. Let's try this little quiz. Good luck. According to kinetic theory, the particles in a gas are what? Are always moving. The pressure a gas exerts on another object is caused by the collisions that the gas particles and the object make. So the containers of a vessel, like the balloon, it's how many collisions the particles are hitting the side, and also how much force, how high a temperature they're at, how fast they're hitting the side. So kinetic temperature is proportional to Kelvin. So we always have to use Kelvin measurements in gas laws because it makes the math work out correctly. Alright, I hope you learned a lot from this one. So this is all about gases. Alright, talk to you soon. Bye-bye.